working with circles is one of the main reasons why I decided to write the text that you guys use. And a big part is once we go through the properties of circles, we can use these properties to demonstrate the majority of the relationships that we're going to talk about later. Most textbooks don't get to circles until, like the last textbook that we used before this one, it didn't talk about circles until like chapter 12 or 14. And so I wanted to introduce it earlier because now, once we work on some properties of circles, we can use those properties to justify or prove some of the common relationships, kind of like the sum of the angles in a triangle and so on. And so I wanted to make sure to introduce these. I also wanted to follow the pattern of the original Euclidean geometry that introduced figures based on the number of sides that, or the number of lines that are used to create them, and circles were the figure enclosed by a single line. So I wanted to start with that. And so even within this, I want to take a look at the anatomy of a circle. Much of this is familiar to you guys. Okay, there's a little box right in the first section that you can kind of copy the things that I'm doing here if you'd like to. Okay, but you should know most of these terms and elements. Okay, so the first is when you define the circle, it's defined as the set of coplanar points a given distance from a fixed point. That fixed point is called the what? The center. Okay, and you can name a circle by its center. Okay, so we can refer to this as circle A. Now, as long as that center is the center of one and only one circle, kind of like the vertex of an angle, as long as it's the vertex of one and only one angle, you can name it with the single point. That's true of a circle as well. So we can call this circle A. Here's the symbol or the notation for that. Okay, and then the other part of its definition is a given distance from a fixed point. So if we look at the given distance is called a what? Radius. Okay, and the radius is designated with a lowercase r. Okay, so segment AB is a radius of this circle. Okay, so again, the other ways to think of it, a radius is a segment with endpoints at the center of a circle and another endpoint on the circumference of the circle. Okay, so the whole set of points that form your circle is called the circumference. And the circumference is just the distance traveled or the accumulated length of the set of points on your circle. So circumference is designated with a capital C, and there's a formula that's attached to the circumference. And with respect to the radius, which we just identified, circumference is twice the radius times pi. Okay, so 2 pi r is the circumference formula. All right, so if you take a segment and your segment has endpoints on the circle or on the circumference of the circle and at the center, that's your radius. But if you take a segment and its endpoints lie on both endpoints lie on the circle, so let's say points B and C here, this element is called a chord. And if you take a chord and you pass that chord through the center of your circle, then that chord is referred to more specifically as diameter. And how does the diameter relate to the radius? It's made up of 2 radii. And so when you look at the diameter, which is designated with a lowercase d, it's equivalent to twice the measure of r, the radius. And so by looking at that, we can go back to that the circumference formula, and we can identify a second circumference formula. We can replace 2r with a d. So the circumference of a circle can also be identified as d pi. Okay? And again, in fact, that's how the pi ratio gets its value. It's just the ratio of the circumference to the diameter of any circle. Okay, so these are all the segments that stay within a circle. Okay, we can take segments or portions of lines that fall outside of a circle and give them a few names as well. Okay, if we take a segment or a line that falls outside of a circle and intersects that circle in one and only one location, okay, that's called a tangent. And the point that it shares with the circle is called the point of tangency. If you have a line that passes through a circle in more than one location, so let's say this line, that's called a secant. And so a secant is going to pass a circle in more than one location, or intersect a circle in more than one location. A tangent is going to locate, or going to intersect a circle at one and only one location. And so what would be this element? Would this be an example of a tangent or a secant? Okay. This would be an example of a secant. And now, even though there's only one intersection shown, and because of the nature of the extension of a line, will this line intersect the circle at another location as well? Yeah, so whether it's shown or not, you extend that theoretical line, it would pass through somewhere down here, and so that would still be considered a secant. And there's no line that is both a tangent and a secant. It's one or the other, or it's a line that doesn't even intersect the circle at all. All right, in addition to these straight segments, as far as the anatomy of a circle is concerned, you also need to be aware of some curved segments. So if you're looking at the curved segments of a circle, so a portion of the circle's circumference is called an arc. And anytime you designate an arc with respect to some angle that intercepts that arc. And so the two angles that we're going to look at are central angles. Okay, a central angle is going to have a vertex that is the center of the circle. So point A would be the center. I'm sorry, the point A would be the vertex. And then the second part to a central angle is the sides of the central angle are radii. Okay, radii is just the plural of radius. And so if we look at this angle BAD, angle BAD has a vertex at the center of the circle, and its sides are radii of that circle. So this is considered a central angle. This central angle intercepts arc BD. Intercepting an arc means that the arc lies in the interior of that angle. So arc BD is enclosed or included within the interior of angle AB or BAD. And now we can also identify an arc with respect to a different angle that intercepts that arc. So again, this arc would still be considered in the interior of another angle, and that angle is this entire angle here. Again, arc BD lies in its interior, and that angle is called an inscribed angle. And in an inscribed angle, the vertex lies on the circle. So the vertex is on the circle's circumference, as is the case with point C here. And this time, what are the sides of an inscribed angle? BC and DC are chords. And so the example in this case of an inscribed angle is angle BCD.